So Hussein, you probably know, but you're muted.
It's not working. This was working just a second ago. Okay, never mind. I'll just use the mouse.
Okay.
Good. Yeah.
Make sure they can hear you.
Can you hear me? I'm on Zoom. Can anyone hear me? That was 40 minutes of preparation. Gail, can you hear me?
We can hear you, Hussein, but you probably it's a little bit low. So.
Oh, okay. I'll raise my voice. This is better. Okay, great.
Okay.
Yeah. Again, thank you all for coming to my dissertation. And today I'm going to talk about accelerating verification of cyber physical systems using symmetry. Serious effort has been spent in the last few years to generate and to manufacture autonomous vehicles. Several companies have promised fully autonomous vehicles by 2020 and 2021. Similar efforts have been spent also to design and deploy autonomous drones. By 2023, FAA and NASA expects that millions of drones will be deployed in the US national airspace. However, these plans have kept falling through because of safety issues that led to crashes and sometimes fatal ones. Also, in the airspace travel field, which is the safest way of travel, still every year there are around 20 near mid-air collisions. These are critical near mid-air collisions where the aircraft are within 100 feet of each other and they avoid the collision just by chance. So you'd expect these en masse would appear more frequently whenever more drones are deployed in the US national airspace, especially in metropolitan areas. So that triggered and motivated several efforts by the government, companies, and academia to design protocols and methods to ensure the safety of deployed autonomous systems, including the UTM protocol designed by NASA and FAA, which ensures strategic deconfliction of paths of different drones, the airborne collision avoidance system that is designed by the FAA and NASA to ensure tactical collision avoidance between different types of aircraft, and NVIDIA with their safety force method to ensure the safety of their autonomous vehicles. In academia, there are different approaches to ensure safety. And the first one is formal methods where reachability analysis is used to formally verify different cyber physical systems. And this will be the focus of the thesis today. There are model checking efforts, synthesis for correct by construction, controllers, software, hardware. There are testing and falsification efforts. These are non-formal but more efficient methods than the formal ones. For example, this is a paper that they changed the color of the obstacle vehicle to trick the object detectors of the autonomous car to trick it to colliding with that obstacle. There is a line of research in machine learning community that is working on falsification, but for ML models called adversarial attacks. And here I'm holding a fake stop sign to trick an autonomous vehicle to kill me probably. And there is also effort to ensure the safety of reinforcement learning agents, both during training and during deployment. This is by no means a comprehensive overview of the literature, but gives a glimpse of the efforts being done in academia to ensure the safety of autonomous vehicles. So in this thesis, I'll mainly talk about reachability analysis. This is the building block for many state-of-the-art verification techniques. In reachability analysis, it's basically a way to predict the future with uncertainty. Given a set of possible initial states, the uncertainty in the initial state coming from sensor or state estimation errors, reachability analysis would compute a set of states that the system will probably reach within a time bound t. So the black trajectory is the one instance of such a trajectory starting from a particular initial state of 0. And you can see the drone inside the green shapes, which represent the reachable set. So the green parts represent the reachable set that does not intersect with the unsafe set. Here, the unsafe set being the walls in the environment. And the red part of the reachable set that is intersecting with the walls is colored in red. So unfortunately, computing exact reachable sets is undecidable. And we know that since the 90s, even for very simple systems with constant dynamics and hybrid dynamics, but with constant continuous dynamics. And since the 90s till now, the formal methods community have focused on developing data structures, algorithms, and tools to efficiently and accurately approximate reachable sets. This is still a very active area of research. Every year, tens of papers appear in several conferences on the foundations of reachability analysis and its applications to verify different systems. In our group, we have developed algorithms, tools, and we applied these tools to different industry-level applications, such as the powertrain verification challenge by Toyota and the satellite control systems by NASA. In the community, also, there have been successes for reachability analysis in verifying an insulin pump and autonomous rendezvous of several systems. Recently, we have been able to verify systems with up to billion dimensions in the community. There is a tool since 2018 by Stanley Buck, who graduated from here. And for nonlinear systems, we're still struggling with 10 to 20 dimensions, taking hours to be verified. So the main issue with reachability analysis is scalability. In this thesis, we're going to use symmetry. So what is symmetry? We know from geometry, these are transformations that would render the objects invariant. In computer vision, these are transformations of the pixel space that preserve the semantic meaning of the image. In dynamical systems, these are transformations that map one trajectory of the system to another trajectory of the system, starting from a different initial state, like rotating and translating the initial state, the position and the heading angle of an aircraft. Lorentz attractor is known to be symmetric to negation of the first two coordinates. This is the type of symmetry that I'm going to use. So symmetry has been useful in many domains. There is this famous quote by Philip Anderson in 1972 saying, "It is only slightly overstating the case to say that physics is the study of symmetry." So symmetry has been used in Dander's theorem to derive conservation law of nature, has been used several times in control theory and in dynamics programming for both reachability analysis and optimal control, has been used for efficient motion planning to compose reachable sets that have been computed offline. In computer science, it has been used in model checking, in early model checkers like Murphy and al. It has been used more recently in machine learning to decrease the sample complexity of computer vision, reinforcement learning, and dynamics prediction. This year's international conference of learning representation, the keynote was on utilizing symmetry or the benefits of symmetry in deep learning that led up to graph neural networks. Also, symmetry is the building block for metamorphic software testing that has been started since 20 years. That is a method in software testing to avoid the Oracle problem. The problem in software testing that requires knowing the correct output for each possible input. And this is avoided by comparing the outputs of tests with two symmetric inputs. In this thesis, I asked the question about can symmetry be exploited to scale cyber-physical systems verification, and if yes, to what extent? Before diving into the details of this thesis, I want to mention several projects that I've worked on that are not part of this thesis. I've worked on deriving minimal bit rates for state estimation of switch systems and systems with inputs. I've worked also on optimizing path and bandwidth allocation in Tor. This is in collaboration with Gerd Delerud and Nikita Borisov and their groups. I've worked also on generalizing digital adversarial examples to physical adversarial examples that can trick actual autonomous cars. And I've deployed also reachability analysis to ensure the safety of an autonomous car that we have here at IUC against collision with pedestrians. So consider this scenario back to our symmetry work. Consider this scenario where a car is following a racetrack. The waypoints in this racetrack are fixed and predefined, but the car is using a LiDAR to avoid obstacles. Consider a similar scenario. Consider a similar scenario where a fixed-wing aircraft has a collision avoidance system that is advising it to go down, left, or right to avoid collision with another fixed-wing aircraft coming from the right. Both of these systems can be represented mathematically as open-loop differential equation, a controller that is providing input to that differential equation, a planner that takes state estimates from the perception module, and the state estimate from the perception model and predefined set of plans to give parameters to a controller, and then the controller would give the input for the actuators to drive the autonomous. The verification problem here is to ensure that the system, starting from any possible initial state in some bounded set, will not collide with any of the unsafe sets. And this, as we said earlier, can be solved using reachability analysis, but the problem is scalability. Scalability to complex nonlinear dynamics, to multi-agent scenarios, complex environments and plans, and the more recent deployment of AI models in perception. So I'm gonna tackle this scalability problem using symmetry. And again, symmetry is are maps that transform any trajectory of the system to another trajectory starting from different initial states. So I'll consider first a very simple dynamical system, not necessarily simple, but it's nonlinear x dot equal f of x that does not depend on any input. Given a reachable set that from a certain initial set of states and another initial set of states shown in orange, for which I want to compute the reachable set, I cache the reachable set in some memory and then in certain cache, and then I transform it to get the reach set starting from the different initial set of states. This will be the topic in chapter 3. And then some dynamical systems will actually depend on other parameters. For example, an aircraft following a segment of waypoints. So given a reachable set computed from certain initial set of states following a certain parameter here, the segment of waypoints, and another initial set of states with another parameter, I use symmetries to transform both parameters to a unified representative parameter. And also I use symmetries to transform the initial sets of states to the same unified representative initial set of states. Then I store the reachable set that I have in the representative coordinates, which I call the virtual coordinates. This will be the topic of chapter 4. And sometimes the system will have to evolve between different parameters. It has to switch according to either time or some condition on the state between different parameters. And the verification question, again, there's an initial set of states, and we want to check if there's any trajectory of the system starting from the initial set of states that will collide with the unsafe set, which is shown in red here. Such a system can be represented as a hybrid automaton and will be the topic of chapter 5. So such a scenario can be mapped to a more or a simpler scenario that is easier to verify and to compute the reachable set for. That will require transforming the parameters and the unsafe sets to more simplified version that is easier to compute. This is the topic of chapter 5 and with a title called abstraction. So let's start with chapter 3. In chapter 3, we will augment state-of-the-art reachability analysis algorithm with symmetry utilization to scale it. This reachability algorithm is data-driven verification. In data-driven verification, we have the same problem setup, but we can estimate the distance between two different trajectories at any time using a function beta that represents the sensitivity of the trajectories to perturbations in the initial state. This sensitivity function can be computed if we have the actual model of the system as a differential equation, or can be estimated using sample trajectories if the system is modeled as a black box model. Using such a function, we can simulate the system from one particular initial state and then generalize that trajectory to surrounding trajectories using that beta. The problem with beta, the sensitivity function, is that over-approximates the sensitivity of the system, and it might sometimes lead to reachable sets that intersect the unsafe set without having a trajectory that is actually intersecting the unsafe set. In that case, we'll need a more accurate reachable set. That where key property of beta comes, that beta goes to 0 as the distance between the initial states goes to 0, which means it becomes more accurate as the initial set of states becomes smaller. So we partition the initial set of states, compute the reachable set from each part, which will make the reachable set more accurate. And in case still intersecting the unsafe set, the reachable set without having the trajectory intersecting the unsafe set, we will partition further and compute the reachable set from each part. If the reachable set is not intersecting the unsafe set, then we can declare that part of the initial set as safe, and then we can compute the reachable sets from different parts of the initial set of state. And then again, and if all the reachable sets are not intersecting the unsafe set, we declare the system as safe. If at some point one of the simulations collided with the unsafe set, then we say it's unsafe, and we have a particular counterexample to provide the design. Such an algorithm has relative completeness guarantees, which means that if the system is robustly safe, the actual reachable set of the system is disjoint from the unsafe set, and there is a distance of at least epsilon between the two sets, then it's robustly safe, and the algorithm will actually terminate with the safe out. If the system is robustly unsafe, which means that there is a counterexample that actually enters the unsafe set, then again, the algorithm will result in unsafe and will provide that counterexample. The algorithm is also sound. So if the algorithm says that the system is safe, then the actual reachable set of the system is not colliding with the unsafe set. If it returns unsafe, then there is an actual counterexample trajectory that it can provide. Now, how can we use symmetry to make such an algorithm more efficient? Before discussing that, we need to define what is mathematically a symmetry of the system. So a map acting on the state space of the system is a symmetry if it commutes with the right-hand side of the differential equation. So partial derivative of gamma with respect to x times f of x is equal to f of gamma of x. This has a very simple proof using the chain rule. For linear dynamical systems, any map that multiplies x by a matrix B, where B and A commute, is symmetry of the system. For example, the trajectory shown in blue can be computed by just transforming the trajectory shown in black using matrix multiplication. So it basically scales it and rotates it. Also, another example, vehicle dynamics, 5-dimensional. The first 2 dimensions represent the position of the car in the plane, is also symmetric to any translation in its position, because the position does not appear on the right-hand side of the differential equation. So the trajectory of the cars going to the right, shown in black, can be transformed, basically translated to get the trajectory of the car starting from a different position. Here, we're going to show how to use symmetry to improve the efficiency of data-driven verification. We add a new cache to the algorithm that is going to store reachable sets. For the sake of the example, assume that the system is scale symmetric to 0.95 times the state. Every time before the algorithm computes the reachable set, it asks the cache if there is any initial set of states in the cache that stores that when transformed using a symmetry will contain the initial set of states that we want to compute the reachable set for. Obviously, at the beginning, the cache is empty, so the reachable set has to be computed from scratch. And then that will be stored in the cache as the root node. The cache will have the tree shape. So the root node will have the initial set of states and the reachable set that we computed. Again, we check if X1 is stored in the cache, or any symmetric version of X1 contains any symmetric version of an initial set stored in the cache contains X1. If not, which is not the case, then we compute it again and store it as a child node in the cache. We continue like that and store the rest of the reach queue or reachable sets. We realize at some point that X7 is contained in a scaled version of X0. Then we can scale the reachable set that's stored for X0 and retrieve that reachable set from the cache. So the key point here is that transforming a reachable set is easier and faster than computing it from scratch because it would require simulation, the computation from scratch and some estimation of the sensitivity, while transforming it is just matrix computation.
Question?
Yep.
So the geometric computation here is there a symmetry such that a symmetry applied to the initial conditions gets me a subset of something in the cache, right? So that might be hard to do.
The transformed version.
So can you go back a slide? I'm just checking I understood what you said, and I'm maybe confused.
Yeah. Okay.
Yeah. So what I have to do is ask, is there a symmetry such that my X7 is a subset of the initial conditions or the initial set for a node that lies in the cache, right?
Yes, actually.
Yeah, that computation could be hard.
Definitely, yes. But for now, I'm using discrete symmetries and they are finite number of ones. But if they are infinite as well for translation, I can choose it according to some algorithms. For example, for translation symmetry, I know where to bring the initial set. I know to translate it to the initial set that I want. But in general, this question is, yes, it's hard to check and can be solved using, for example, optimization algorithm.
Okay.
Does
that allow you to say anything about when it's better to use a cache and when it's better to just recompute the thing?
This is definitely a very interesting question, and we'll see in the experiments that sometimes the overhead of caching reach sets overcomes the benefits of transforming them. And this is especially in the case where we have few symmetries and discrete symmetries, where we will not always find after search that there is a reachable set that is stored in the cache using just one transformation. But with continuous set of symmetries, if we have a group of continuous, like a continuous set of symmetries, it is more easy to find a reachable set that is actually stored in the cache that I can retrieve.
Excellent. Thank you. Thank you. That was helpful.
Hussein, also had a question I think you partially started to answer because you said you're thinking primarily of discrete symmetries. I was thinking of, like, there are some symmetries that are more common than others. The one I was thinking of in particular would be dilations. So you have sort of quasi-homogeneous vector fields, the dilations, maybe different dilations, different dimensions with the invariant, right?
Yeah.
So so far your discussion seems to just say gamma, whatever it is, right? Doesn't depend on the structure.
Yeah.
Do you have some results where certain symmetries are more helpful?
Yes, actually, in the experiments, I'm showing the translation symmetry, which is very obvious symmetry about the cars. And that what is actually resulting in significant savings in the verification time. But this scaling symmetry, for example, for the circular dynamics, or for the Lorentz attracted just reflecting initial set, you'll have to match exactly the initial set, like a reflected version of the initial set, which is not always the case. But if we have continuous symmetries, then we can move it exactly to that position.
Okay.
We can choose, like, there's a range of symmetries that we can choose that particular symmetry that will transform the needed initial set to the one that is stored in the cache. This is not always the case if we have few discrete symmetries.
But scaling, I'm thinking scaling is like a parameter family of symmetries, right? It is continuous, right?
Yes.
You could use that, right?
Right. So here I'm fixing one, but in general, yes, actually I can get all of the reachable sets there using that continuous scale symmetry.
Okay. We can talk more about it.
This is maybe also along the same line about your questions. Sometimes you can decrease the initial set of states without the use of the cache. So if we have a group of continuous symmetries, we can select subset of that group and decrease the dimension of the initial set of states and compute the reachable set for the smaller initial set or the lower dimension of initial set, which is much easier. And then add the initial set in these dimensions to the computed reachable set to get the needed one. An example is the car example. So consider the case where we need to compute the reachable set of the car starting from a range of positions and range of heading angles. Because we have continuous symmetries in the position, we can compute the reachable sets just from one particular position with the range of heading angles, and then move that reachable set in different directions to get the reachable set from the range of positions. So here it would eliminate the need of the cache, and that is also along the same with the scaling symmetry. I can scale the whole initial set to a smaller initial set and compute the reachable set without the need of a cache. So the guarantees of the algorithm, the cache augmented algorithm, is inherits the reachability, the guarantees of the original reachability analysis used to compute the reachable sets from scratch. So if the original reachability algorithm is sound and relatively complete, then the cache augmented algorithm is also sound and relatively complete. So here, the circle dynamics show the reachable sets computing using DriveR1 of the state-of-the-art tools to compute reachable sets that have been developed in our group. The green to yellow is a reachable set that's computed using DriveR, and the brown bar is the unsafe set. On the right, I'm showing the reachable set computed using the cache augmented method, using the 0.95 scale symmetry. And blue to violet is the reachable set that is retrieved from the cache. Here, using just one particular symmetry, for example, permutation, negation for different systems, will result in verification times worse than DriveR itself because the cache overhead will overcome the benefits of transforming one or two reachable sets out of hundreds. But when we have continuous symmetries, similar to the translation symmetry, while using caching or abstraction, dimensionality reduction of the initial set, then we will have significant reduction in verification time. We have order of magnitude or 2 orders of magnitude reduction in verification time using caching. And when we reduce the initial set of states, then we have another order of magnitude. Here for the I'm verifying two cars that they will not collide with each other on the same lane. You can see that only small part of the reachable set has been computed from scratch and the rest is transformed. Also, this is another scenario where the two cars are braking. When we reduce the size of the initial set, then only one trajectory in these dimensions is actually computed from scratch, and all the reachable set in these two dimensions, the positions of the cars on the lane will be retrieved from the cache. Or not the cache, will be like enlarged using the symmetry. So the summary, we introduced symmetry caching into data-driven verification. We introduced the cache tree data structures to store multi-resolution reachable sets, and we used symmetries to increase the cache itself. And we showed experiments with significant speed up in verification time. Now let's start with the new chapter. If you don't have any questions, I don't think we have time. Yeah. So there's we go to the case, more general case, where the dynamics depend on a parameter that is being followed. We consider this example scenario where two aircrafts need to navigate a shared environment. Again, the dynamics of the aircraft can be described using differential equations or black box models. There is a set of possible initial states because of sensor or state estimation errors. Predefined plans that the agents will follow in the environment. These can be designed using RRT or any other planning method. And there are other fixed obstacles. And the question is to check if the agents will collide with each other or with any fixed obstacles in the environment. The dynamics of the agents can be described using very simple can be simplified to be represented in four-dimensional differential equations representing the speed, heading angle, and the position of the aircraft in the plane. Each aircraft would have a segment following controller that is dependent on the segment being followed, and the relative position of the aircraft with respect to that segment using the current cross-track error. To verify such a system, we can use existing reachability analysis techniques where we need to compute the reachable set for each mode sequentially. So for each mode, we would simulate the system and then estimate its sensitivity or compute it, and then load that simulation with the reachable set. And since the agents here, the dynamics of the agents are non-interactive, then we can compute the reachable set sequentially between the two agents. But the question is, can we do it more efficiently using symmetries? Again, we define symmetries, but now for the more general differential equations where we have a parameter. The new condition would add the need for a new symmetry. So a map now, gamma, acting on the state space is a symmetry if there is another map acting on the parameter space that will satisfy the same condition as before, that the gamma and f compute. So the partial derivative of gamma with respect to f times f is equal to f of gamma of x rho of p. This has the same proof as the autonomous one, where we don't have a parameter using the chain rule. An example symmetry for the aircraft example that we had would transform the segment being followed to be to a new coordinate system where the segment is aligned with the y-axis and ends at the origin. And the gamma of that symmetry would keep the speed the same, translate the heading angle with the rotation angle of the coordinate system, and transform the position of the aircraft to the new coordinate system where the segment being followed is the y-axis. So the trajectory of the because of the windows. So the trajectory of the aircraft following the jth segment can be transformed to a trajectory following the y-axis and ending at the origin. Now consider the case where we have a family of symmetry maps. So each segment in the environment for each agent, we have pairs of symmetries, gamma p, rho p, that would translate it and relate it to be in unified format, here the y-axis. So for using the virtual map, we define a new map just for simplification that maps every segment or every parameter to a representative parameter, which is rho p of p. Since pj and pj plus 1 have the same length, then using translations and rotation will be represented in the same segment in the virtual system, virtual coordinates, which is aligned with the y-axis and ending at the origin. So the trajectories of 3 fixed-wing aircraft will be represented as several segments of trajectories following the y-axis and ending at the origin. So here I'm describing what will be the use of symmetry in multi-agent verification. So again, we have a cache for reachable sets, and we start computing the reachable set for each agent sequentially. First, we check if the cache has a stored reachable set that is in the unified format in the virtual system. So at the beginning, the cache is empty. So we compute the reachable set and transform it to the unified coordinate and store it in the cache in the virtual system. Since P2 has the same length as P1, then the reachable sets of P2 and P1 are represented in the same cache entry in a sense. So if we want to compute the reachable set of P2, we check first if the reachable set has been computed before and stored in the cache. Sometimes part of the reachable set is computed. So we retrieve that part and then compute the other from scratch and store it in the cache for later use. At the end, this would be the shape of the reachable set where different modes with the same length will be represented with the same entry. So here P1 and P2 have the same length, P4 and P5 have the same length, and P3 and P6 have the same length. So each of these two will share reachable sets, and since the dynamics of the different aircraft have the same dynamics, then they will share reachable sets as well between them. So our reachability analysis algorithm is sound. It will over approximate the reachable set of the system, the exact reachable set of the system, but the completeness is not guaranteed because of over approximation error in the reachability subroutine used. Because of guards intersection, these are the sets of states that define when the agent reached the waypoint, and there are over approximation errors because of the grid-based caching of the initial sets. The last one can be solved using subset of reachable sets computation that was presented in HSCC last year. We implemented this algorithm in a new tool called Cache Reach, and this is the reachable sets for the 3 fixed-wing aircraft example that we have shown before. The left shows the reachable sets stored in the virtual system. This is the cached reachable sets. We stored 1,500 reachable sets using our computation, and we retrieved 500 to compute the reachable sets in the original coordinate. We tried cache reach on different scenarios with different numbers of agents, both linear and nonlinear agents, and we achieved 66% reduction in verification time, or speed up in verification time. You can see going from 22 agents to 3 agents, we did not have to compute any new reachable set, 90 and 90, but the number of reachable sets retrieved increased by 100. So in a summary, in chapter 4, we introduced the concept of virtual system. We implemented the algorithm in a new tool called Cache Reach, and we showed experiments that show 66% speed up in verification time. This would be a good time.
Yeah, response to see if there are any questions.
Any questions? Okay, then let's move to chapter 5. Here we have to represent scenarios using hybrid automata, and we will introduce a new counterexample guided abstraction refinement algorithm. So cigar algorithms are a type of algorithms that follow the same format. We have a model, an unsafe set, or a property to be verified. The abstraction subroutine of the cigar algorithm would result in a smaller and abstract model and unsafe set that is easier to verify. Then the verification subroutine will verify the smaller or abstract model with the unsafe set. If the verification subroutine says that the system is safe, then we have a proof of safety. The reason that we can verify the safety for the smaller model, because every behavior of the original model can be mapped to a behavior of the smaller or abstract model. So if the smaller model is proved to be safe, then the original model is safe. However, if it says that if the verification routine says that the system is unsafe, then it has an abstract counterexample. Then there is a subroutine to check if this abstract counterexample corresponds to an actual counterexample of the original model. If in that case, we call it spurious. So if the counterexample is not spurious, then we have a set of concrete counterexamples that are proof of non-safety of the original model. And if the data check results in that the counterexample is a spurious one, then there's a proof for that counterexample for being spurious, which can be utilized in the refined subroutine that will result in U abstraction that eliminates the spurious counterexample and results in a tighter over approximation of the original model. So in this thesis, I'm introducing a new cigar type algorithm using symmetry. Again, consider a very simple scenario where there is a drone that's following a plan with 6 segments. Such a scenario can be represented using a hybrid automaton with X being the state space of the dynamics of the agent, P being the parameter space containing the 6 segments. X0 is shown in green here, representing the possible sets of initial states. P0 is the first segment to be followed. E represents the set of edges or consecutive segments in the scenario. Guard represents the sets of states associated with each of the edges that determine when the agent is said to have reached the waypoint and can switch to following the next segment. Reset is identity because the state of the agent will not change if it switched following segments. And F is the right-hand side of the differential equation, representing the dynamics of the agent. O, the unsafe set, in just for generalization purposes, now it's a map instead of a set. So it maps every mode to corresponding unsafe states for that mode. So that scenario can be represented using a hybrid automaton with 6 modes, representing each segment to be followed. Again, we use the same concept of virtual map from chapter 4. So we have a family of symmetries, pair of symmetries for each segment or mode in the environment. So we map first, before reachability analysis, we map segments of the same length. For example, if you are using translation and rotation, the symmetries, and we have that aircraft example, to the same abstract mode. So the idea of the abstraction mapping all symmetric modes to the same representative abstract mode. And then we'll map the edges, guards, and resets to their representative ones in the abstract mode. Then we can use this forward simulation relation to map any execution of the concrete automaton to an execution of the abstract one. Okay. But not necessarily vice versa. So there might be a trajectory of the abstract automaton that does not correspond to an execution of the concrete automaton. So for the scenario that I've shown in a couple of slides ago, the first segment is shorter than the other segment, and all other segments have the same length. So in the abstract scenario, it will have only 2 segments, PV0 and PV1. PV0 representing the first segment to be followed, and PV1 representing the rest of the segments. And the unsafe sets would represent the relative positions of the original unsafe set with respect to the segments represented by each abstract segment. Segment here, I'm using interchangeably with modes parameters. So we have a new abstract hybrid automaton that has only 2 modes instead of 6. that is easier to verify. So we can compute using existing reachability analysis techniques for hybrid automata, the reachable set shown on the top. Just for visualization purposes, I'm mapping that reachable set to the concrete scenario. You can see that there is a spurious counterexample there. Obviously, the drone cannot jump and start from the unsafe set and then follow the vertical segment. So this is just a result of the abstraction and the over-approximation behavior, the abstract automaton over-approximating the behavior of the automaton. So the check of spurious examples subroutine of my Sibai algorithm would be depth first search based. It will search over the concrete automaton guided by the counterexample. And for each sequence S of pairs of parameters and trajectories represented by sigma b, which means that if I apply the forward simulation relation to S, I would result in the counterexample sigma p. It checks if the initial state of that sequence is in the initial set of states, if all the discrete transitions are legal, which are allowed in the concrete automaton, and the last state belongs to the unsafe set for that particular one. Very important here is to see that the abstract automaton does not over-approximate the behaviors in the continuous dynamics because they match exactly using symmetry. They only over-approximated in discrete transition. This is in contrast with other cigar-based algorithms for hybrid automata, where they combine continuous dynamics together, so they also over-approximate the behavior in the continuous dynamics part of the hybrid automata. The refinement step is also depth first search based, guided by the counterexample, and it starts from the unsafe set going backward. So start from the last mode visited by the counterexample, and then recursively splits that abstract mode to eliminate any unallowed discrete transition and spurious counterexample, spurious unsafe sets. So to eliminate that particular spurious counterexample that I've shown for the scenario, the abstract mode PV1 would be split into two modes. Now, each mode representing part of the segments of the scenario. The original PV1 had P1 till P5, now PV1 representing P1, P2, and PV2 representing P3, P4, P5. And in the abstract scenario, we would have two segments of the same length, PV1 and PV2, but they would have different unsafe sets shown in orange and violet. Okay. So, and they will have different guards and beasts. So this scenario captures more accurately the concrete scenario. And you can see that the reachable set now, for going to the right, has a different mode than going to the left. And they are represented using different reachable sets. So you can see if we map the reachable set to the original scenario that the spurious counterexample got eliminated. So our spurious counterexample, our cigar algorithm is sound and complete, relatively complete. So the check for spurious counterexamples would return all concrete counterexamples represented by the abstract counterexample and nothing else. The refinement step will eliminate the counterexample in just one call for that refinement subroutine. And the cigar algorithm inherits the same guarantees that of the verification subroutine. So if the verification subroutine used for the abstract content is sound and relatively complete, then the cigar algorithm is also sound and relatively complete. We implemented a weaker version of this cigar algorithm in a tool called Scene Checker. The difference is that the refinement algorithm does not eliminate the spurious counterexample in just one step. And we applied it to different scenarios. This is a particular scenario where the drone following a plan with hundreds of segments shown in black. In this part of Chicago, the gray are representing buildings. This quadroter has a 6-dimensional controlled by a neural network. If we want to verify such a system with no unsafe sets using DriveR, the existing tool, then it will say safe after 53 minutes. So without unsafe sets, you don't need even partitions of the initial set of states. So you will compute the minimal number of reachable sets. Still, you need 53 minutes. If we're using scene checker but without refinement, then it will say unsafe just in 1.8 minutes, because the over approximation error of abstraction is leading to the reachable set colliding with the unsafe set. But with refinement, it can say safe in 7.2 minutes. Still much faster than the original driver. On average, we achieved 14 times speed up on driver and FlowStar, two of the leading tools for hybrid systems verification. And in all of the cases, scene checker was faster than driver and FlowStar. There is a small digression here.
Just to keep an eye on the time. Some of the committee members might have to have a hard stop at 5. So maybe skip this part and
I'll
to the last piece.
So summary. We have a cigar algorithm that's based on symmetry to accelerates verification of autonomous system and eliminates the need for a cache of reachable sets that was needed in chapter 4 for similar scenario. And we have a Python tool, scene checker, that implements a version of this algorithm. And I skip this summary. So we tried in the past few months to apply symmetry to a real life example. The video of the fixed wing aircraft that's shown before, and I'll show it again. So here the fixed wing aircraft simulated in Gazebo and the robot operating system ROS has a collision avoidance system brought by, we got it from NASA and FAA and Johns Hopkins University that are developing this protocol that tells the fixed wing aircraft to, with different advisories, climb or descend or go left or right, to avoid collision with other aircraft in the airspace. Such a scenario, in a more abstract sense, these are the trajectories of the two aircraft in the scenario. I'm showing only the one going from the left, and that is the on-ship trajectory going up. I'm plotting Y versus X, and the trajectory of the intruder coming to the left. The red dots represent the places at which an ACAS advisory was given to, and you can see that at time 1 second or 1 minute, the ACAS told the intruder to descend and then told it to climb to avoid collision. This ACAS system has a neural network version to decrease the space needed for deploying such a system on small drones, and has been tested and verified both in open loop and closed loop, but with very simple ordinary differential equation dynamics. And we were asking the question if we can use symmetry to accelerate high fidelity simulation, which is a more accurate way to evaluate such a system. So in our challenge problem setup, we can represent such a system again in the same way that we have a controller, differential equation, and the environment, other aircraft represented using a high fidelity simulator, Gazebo and ROS. The perception module represented by the surveillance and tracking module of ACAS, and the planner part is represented by the ACAS threat resolution module. The ACAS would update its advisories at 1 Hz frequency. So every second it would take the estimates of the positions and relative heading angles and velocities of the different agents, and then estimate their state and feed it to the threat resolution model, which will provide desired velocity vectors or advisories to go in different directions to avoid collision. And as I said, this has been tested and verified both in open loop, like the ACAS system itself, and in closed loop in very simple dynamics. So high fidelity testing of autonomous systems in general is expensive, but it is cheaper and more safe than field testing. It is more accurate than low fidelity verification and testing. And it's needed as a regression test. Every system update, you'll need to run a new test suite, the same test suite again and again, which is expensive, even for in the simulation environment. So how can we use symmetry to improve the efficiency of high fidelity testing? Before going into the detail how we are using symmetry, there are several challenges and extensions in which this example is different from the rest of the thesis. We have interacting agents instead of non-interacting ones. We have high fidelity simulators instead of ordinary differential equations. We don't have predefined plans or paths that the agents will follow. Instead, we have a software, complex software, that's the ACAS or a neural network. We have non-determinism simulation. We simulated the system from the same initial state over and over again and resulted in different trajectories. This is a key assumption in the reachability analysis algorithm where we had to have sensitivity function. But if the same trajectory, if the same initial state is resulting in different trajectories, will make the sensitivity infinite. So that is a key problem in verification, for example, if we are going to verify such highly complex model. So we have non-determinism, and we did some metamorphic tests where we rotated the initial states and we simulated the system expecting that the trajectories would be rotated versions of each other or reflected or translated versions of each other. They weren't, but they were close enough. So also this is a challenge. The system is not fully symmetric, but partially symmetric. And we will need to account for such non-symmetry in our analysis.
Okay. Do we know all the sources for non-determinism?
We have done some experiments to figure out the source. One of them for sure is the delay. So I am saying here that the ACAS system updates its advisor at 1 Hz, right? But different components are communicating over the ROS operating system. So there is network communication there. And there are delays in that network communication between even the components of ACAS, the threat resolution and the surveillance and the tracking module, and between the ACAS system and the actual dynamics of the agent. So receiving an advisory to go up at slightly different time will result in a completely different project.
Okay.
Yeah, and this is just before the last slides. We have different, in that efficient testing framework using symmetry, we have different components, the test suite, which is a list of initial states for different agents that is gonna be executed every system update. There's the ACAS SXU, and we initialize a cache, but now instead of reachable sets, we have a cache of trajectories. 1 second trajectories following the 1 Hz updates of ACAS. And we still have the high fidelity simulator. So every time a test suite gives a test case representing the initial states of the different aircraft, it will ask the ACAS SXU for an advisory for the different aircraft. Then we'll check the cache if it has the actual trajectories or a symmetric version of these trajectories stored in the cache. If it is, then it's retrieved from body coordinates or the unified representative virtual trajectories to the world coordinates. And we'll ask ACAS SXU again for a new advisory for the next 1 second. This is again following the 1 Hz update of ACAS SXU. Once there is a cache miss for any of the for any of the agents in the scenario, then we stop and ask the high fidelity simulator to simulate the rest of the scenario. And then cache all of the trajectories in the representative format in the cache. We did some experiments, preliminary experiments, and we have few results. We tried different symmetries, 1D rotation, plane rotation. There's also 3D rotation that's to the body coordinates of the aircraft. We achieved 21% reduction in number of 1 second trajectories that need to be simulated when we don't stop after the cache miss, but we still have a problem with the case where we stop after the first cache miss. And there are different ways to tackle this. One of them is using reachability analysis. So back to our challenge problem. For the scalability of reachability analysis to nonlinear dynamics, we introduced symmetry-based caching of reachable sets for data-driven verification. For the multi-agent scenario, we have the virtual coordinates concept in chapter 4 that shares reachable sets between different modes and different agents. In complex environments and plans, we have the Sibai algorithm and the virtual coordinates in chapters 4 and 5. And one key point is that when we verify an abstract scenario using a Sibai algorithm, this is generalizable to any plan, to any other plan that have the same abstract representation. So you can generalize a verification result to other plans. And for AI models in perception, there is the part that I skipped over about enforcing symmetry on neural network controllers in closed loop systems. And there is the symmetry-based efficient testing for the ACAS SXU as a particular application. And that's it. And finally, I would thank Cheyenne for his guidance and help throughout the years, and for the committee members for their advice and help and the letters that they have written so far, and for the friends for attending and other collaborators for helping throughout the years. I'm happy to take any questions.
Great, thank you very much. So first of all, from the audience here, thank you for joining us today. Any burning questions that you would like to ask right away? Going once. Okay, go ahead, please.
So in the system where like you don't have a symmetry zone, or like the system is not symmetric, how do you like almost identify the law of symmetry? Do you use like, so this system is not based on models, right? Just based on some.
Oh, yeah. I'm not checking if the system is symmetric. I'm assuming that the system is symmetric, and the user that is asking me to verify such a model will provide me with the symmetries.
Okay.
But for the ACAS SXU example, or for general, maybe high fidelity simulation, I'm doing that metamorphic testing about I check the output of the system with different symmetric inputs and check if the output of the system is actually symmetric.
So you don't have a way to identify.
That is like simulation part, but for the mathematical part, there are the conditions that are shown on commutativity.
Yeah.
Right? So you can, if you have the differential equation representation, you can actually check mathematically, or there's also the eventually you will need like some learning algorithm or like some optimization based algorithm that will figure out what are the symmetries. And that's not what's happening in machine learning. Also in machine learning, they assume that the system is symmetric or the neural network should be symmetric, and they are kind of trying to enforce symmetry. So this is it.
Because it's very similar to non-dimensionalizing a physical system. If there is a way to learn how to, this would be interesting.
I don't know much about them.
We can come back to more questions from the audience. Let's go around with the committee members.
Yeah.
Some of them might have some hard stuff. So I'll start with those of you who are online. David, do you have any questions? Further questions?
Thank you. I've got two questions. They're both sort of open and formal speculative questions, but I'd love to hear what you have to say about them. So the first one is dynamical systems can do horrible things to measure. So imagine I have an initial set, small changes in the initial set, once I've floated down a dynamical system, can get very badly mangled. For example, I might end up, and that could really mess up your caching strategy, right? So your argument essentially says, if I have in my cache something whose start set contains the start set I'm querying under symmetry, then I can just fish it out of the cache. But if the dynamical system really mangles up the measure, doing so might not help me very much, because it'll be difficult to draw conclusions. Question, it seems to me off the top of my head that the presence of a symmetry means that that effect must be contained in some way. And I'm curious whether that's the case, whether you know anything about that situation.
Contained? Well, I'm not sure what you mean by contained.
Well, so if my dynamical system is symmetric,
Yeah.
there have to be some things it can't do to the initial set.
You mean when it's propagated through the, like,
Yeah,
when
through
it
the
evolves,
dynamics.
when you apply it
Yeah.
over and over again. So you're, yeah, just to get the question right. So when you update the, you apply f of x over and over again,
Right.
you change the format of that set, right? You start with probably a rectangle, and then you end up with a sphere or this joint, not this joint, but there's continuity there. So it will be changed in form. The key thing in reachability analysis in formal methods, they assume a data structure that will represent these sets. So you will have a sequence of sets, and whenever you have this change in shape in a weird way, you would over approximate it using that shape. So if you're using hyper rectangles to store the initial set, you would over approximate the states with the hyper rectangle.
No, I'm aware of this. I'm with you there. I understand this sort of, you can make this safe, but of course at cost of efficiency. And the question I'm asking is, does the presence of a symmetry make any of this stuff easier?
I understand the question, right? David is asking you about the first theorem which allowed you to move reach sets. So if the symmetric system is symmetric, you are allowed to move not just individual trajectories, but the entire reach set.
Yes.
So symmetry, and if there is such a symmetry, then you can move the reach set sound.
Right.
That's what I think David is asking.
Yeah, that's the argument. But it also suggests that your reach sets behave in
different ways.
badly tangled.
I think one of the answers is reduction of the initial set. So when we say that we can reduce the initial set in, like, reduce the dimensionality, removing the dimensions that are symmetric, right? For example, in the translation symmetry of chords, you can just remove the initial set, uncertainty in the initial set for these symmetric dimensions to just one point. And then you can just add that uncertainty to the reachable set that is computed for the initial set where these dimensions are just one, right? So in a sense that, yes, enforce a shape of the reachable set.
Yep.
That shape is adding that initial set in these two dimensions across the reachable set. So it's uniform across the reachable set.
Okay, so now we have, sort of an argument that at least some kinds of symmetries in dynamical systems make all sorts of geometric computation easier, as well as this caching process and the like. Can you characterize the good symmetries versus the bad ones?
Yeah, I have very vague judgment here. That is like, if you have discrete symmetries, then usually I'm using, even if the system has continuous symmetries, I'm using sometimes discrete symmetries. When you have discrete symmetries, it's hard to match. I think the key for saving is not caching. The key for saving is reduction in the initial set. And that will enforce the shape to be in a certain way, as you said. It's decreasing so in the translation symmetry, you can obviously make the position just one point instead of a range, because the position is not appearing on the right-hand side of the differential equation. So it's easy to do dimensionality reduction. Sometimes it's not as easy. For example, in the linear case, you have any commuting matrix D is a symmetry. This defines a subspace that you can do reduction to a new initial set where you remove that subspace from the initial set. How can you do that with for an initial set that affects all the dimensions in the sense? So you result in new initial set that's affecting all the dimensions, but is resulting in a lower dimension initial set for which you can enforce. Now you compute the initial set for the reduced initial set, and then you plot it using that simple addition. And that will enforce the symmetry, not the caching. The caching will add, as you said, the overlap extension error because of the data structure representation. So characterizing good versus bad symmetries, I'd say whenever we have continuous symmetry, then there is some dimensionality reduction possible.
I think there's a rich topic here.
Yeah.
Right. And I thoroughly enjoyed the talk and found it very interesting. But I just draw your attention to the question of who's good and who's bad as being something where, one could do quite a lot of quite illuminating theoretical work.
Yeah.
I'll pass to the next question. Thank you.
Thank you very much, David. Appreciate the comment. Gare, would you like to go next, please? Any questions or comments?
Yeah, sure. So in dynamical systems, you kind of focused on uncertainty in the initial state, but other places you get uncertainty is from sort of the inputs to the system, like noise and so on, or from the dynamics themselves, right? The model's probably not going to be exact. Any thoughts of sort of generalizing your work to, say, the case where F is not necessarily accurate or where you have noise?
Yes. So the simple generalization to parameters is shown in chapter 4. But as you said, there might be some disturbance. There is work by Murat Archak and John Mathers that consider reachability analysis for discrete systems. So it's different setting and here. That setting for dynamic programming for discrete systems has some disturbance. The condition there is that the dynamics should also be symmetric to the disturbance. So similar to here, we would have like rho of P. So initially we had only GROM that act on the X. And then we added rho that should act on P. So when there is a disturbance, there should be a symmetry acting on the disturbance part, or the effect of the disturbance on the dynamics themselves. And if the system is not perfectly symmetric, we've been thinking long to include that as part of the reachability analysis. So as you said, like including the uncertainty propagation, not just because of the initial set of states, but because of the disturbance factor. But yeah, neither of them has been rigorously followed by us. But I'd say that we can generalize them following the same method that Murat had done with the John.
Great, thanks.
Okay. Thanks. Thanks for the question, again. Sasha, you had the other committee member online. Questions and comments.
All right. First, Hussein, very nice work. Thank you for presenting it. I had a couple of questions about your final part about testing.
Mm-hmm.
So first, you mentioned non-determinism as one of the key concerns here, right?
Mm-hmm. Yeah.
So can you elaborate a little bit more of about when is non-determinism useful here, and when it's not, or what prevents you from just setting the seeds for every simulation that you do? And yeah, would it be just the solution for any problem you have or not?
Yeah. Actually, there was an effort by Chao to make the simulation in Gazebo deterministic. I don't think it was successful. Was it successful in making it deterministic?
I think the main source of non-determinism is mentioned in that this network delay
Yeah.
used
So
by
there's
even
no-
on the same server. We can minimize it. We never really been able to have a way to control it.
yeah, there's no seed to fix basically to eliminate delays. But the non-determinism problem would, for example, prevent us from using DriveR. So DriveR is built for black box models. You simulate, and then you estimate the sensitivity. But if you have from the same initial state, two different simulations, that will make sensitivity infinite. And that will eliminate, for example, that part of reachability analysis, unless we account for that non-determinism as part of our analysis. Even that will not be an issue in our efficient testing scenario, because we are caching, and the cache will be grid-based as well. So whenever we want a trajectory, we're not searching for that exact trajectory starting from that exact initial state. We will quantize it. So in our efficient testing algorithm, we're adding non-determinism itself. The retrieved trajectories will not be exactly matching the actual simulation with the alarm, which plays to our advantage. In a sense, if the high fidelity simulator is resulting in non-deterministic simulations, so might as well, if we retrieve not exactly the simulation that we would expect from a high fidelity simulator, then it's still okay. If we still can bound the error in a certain way, right? So that is marketing
So
advantage.
to summarize, as if the window to verification closes because of non-determinism, maybe another window to
Testing happens, yeah.
That's fine. Just for the record, having non-determinism and having to deal with it is definitely better than just saying, "Oh, I'll just fix everything and live in this much simpler but also less realistic world." So
Definitely.
nothing else, non-determinism is a factor that when you address it in the right manner, is improving the realistic nature of testing. So
this is what the actual system will be deployed. It will have delays, so we might have delays.
All right, very good. I guess I had another quick question on when you use metamorphic properties, and when you are setting up the testing your tests. I'm curious, how have you ever encountered something like false alarms compared to your simulation, but also compared to the real world? I know it's hard to have the real world evaluation on the actual aircraft, but even for simulation, did your tests have any false negatives, any false positives?
Yeah, so for false negative and false positive, we would have a concrete metric for evaluation of a test. We don't. We only are subjectively judging if the trajectories make sense. So in metamorphic testing, we're just checking if the simulations of the two aircraft following their waypoints will result in advisories similar to a rotated version, right? Because that advisory should not depend on the absolute coordinate system in which these agents are represented. They only depend on the relative coordinates. So if you rotate both agents, definitely you didn't do anything in the real world, you just represent in different coordinates. Then I check if the advisories of ACAS are given at the same time and are given with the same advisory, go up, go down. It was not. Sometimes if you rotate the trajectory, different advisories are given at different times. So it's hard to say this is because of non-determinism or because of non-symmetry of ACAS. But that said, the neural network version of ACAS has some plots in Stanford paper that represents the different advisors in different parts of the state space. You can see that there is non-symmetry in the protocol itself, at least the neural network version. So sometimes if you slightly deviate from the center, you would give like right advisory where it should give left advisory. So yeah, to answer the question, we don't have concrete metric. We're not evaluating these tests like collecting numbers of correct outputs or non-correct outputs. We don't know what's the correct output of ACAS. This is the Oracle problem. We wanted to just avoid collision in the closed loop scenario. So we're just checking if the actual aircraft would collide with each other at the end of the night. They're not. So in all of the scenarios so far that we tested 97 simulations. None of them led to collision of the two aircraft. So it's working in typical scenarios fine.
Okay, sounds good. Thank you. That's all from my side.
Thanks for the question.
Okay, thanks, Sasha. And Daniel, now we're back into the room.
Yeah.
I think I'm okay.
Okay, great. All right. Well, then we are in this stage where the committee gets to discuss quickly what happened. So everyone gets to step out again, including yourself. Yeah, thank you.
I mute you. And
Should we go to the room one that you invited us?
Yeah, I created that breakout room and you can join us there. I'll just walk over there. Don't mute it.
okay.
This thing doesn't seem to be working. And you can answer more questions outside and then we'll have the access to that.
Thank you. Yeah, thanks, Sasha. Thanks, Gary. Can you hear me?
Yeah, congratulations, Hussein.
Thank you for all.
Congrats, great job.
Thanks, Sasha. And thanks all for coming.
Okay, bye, Hussein.
Thanks, bye. Bye, Sasha.
Thank you, bye-bye.
شكرا جزيلا يا جماعة. بطل في حدا.
I think there was a discussion, you know, your work, and I contributed some comments.
شكرا لك.
I mean, I'm totally fine with it. Okay.
شكرا لك. نشوفكم إن شاء الله. شكرا يا مصباح. أميرة.
It's not like I'm sitting here saying, oh, you guys didn't invite me co-op. No, it's not it's a privilege and an honor to have you as a.
I'm on spot.
Whatever. I learned that from Eddie, whatever you talk, whatever. It's a great response. It really works. How many is it for you? No. How many graduates? That's six. Six? Okay. I thought it would be actually the more than that. No. When did you join?
The driver thing, no?
2008. So you started graduating maybe by like 13, 14. Yeah. So, okay, roughly like once a year, maybe. Yeah. How about you? I check it.
خلص. برجع.
It's easy to check it because I have a list. Would it be more than that?